I'm happy to introduce the last speaker of today, and that's Yasunori Nomura, and he will talk about from the black hole conundrum to the structure of quantum gravity. Please go ahead.
Okay, thank you. So do you hear me?
I hear you. Yeah, I hear you.
Okay, cool. So thanks the organizers for the invitation. Today I'm talking about some implication of black hole physics to the structure of quantum gravity we have recently learned. So let's start from reviewing some basic history. It's completely well known, but to set the stage of today's discussion. So as we know, two pillars of modern physics, quantum mechanics and general relativity, do not get along too well. Okay? But there are two qualitatively different problems in merging these two theories. One is at short distances, as is well known. At the Planck distance, the theory loses control, and you have all kinds of quantum corrections, and so you need the infinite number of counter terms, and then you lose the predictivity at the short distance. This is the regime where conventional definition of string theory will be able to address well, and you can calculate super Planckian scattering and so on, and you can get the finite answer. But there are also the problem. It seems to be a structural problem of quantum gravity at long distances, even long distances, and you have some problem collectively called the black hole information problem. And this is the one we will be talking about today. Okay, so what's this black hole information problem? Because the problem is not necessarily in the form Stephen Hawking presented. So it's good to review what really the problem is. Okay, so that problem has to do with the third pillar of modern physics, statistical mechanics. As is well known, Bekenstein asked, what happens if you drop some object, for example, some radiation, which has an entropy. If you drop this to the black hole, and the black hole doesn't have any hair, it doesn't show any detailed information. So if this radiation is absorbed into the black hole simply become bigger black hole. And if black hole does not have entropy, then the second law of thermodynamics would be violated. But he proposed that that's not the case. Black hole has an entropy which is proportional to area in Planck unit, because of the area theorem that black hole area of the horizon simply monotonically increases during the process of merging and so on. And indeed, he can show that this area term plus matter entropy, this whole entropy is obeying the second law of thermodynamics. Okay, but then Stephen Hawking came, this may not make any sense, because if the entropy is there, in the case of short-seed black hole, it's like 4 pi m squared in Planck units. And if you take a derivative with respect to energy, which is m, mass, you have to have a finite temperature. But if black hole is simply just absorbing material, then of course it doesn't radiate, and then of course temperature should not be there. So he started calculating, including quantum effect, and then suddenly he found famous Hawking's radiation. But an important point I just want to share as a starting point of the discussion is his assumption. Essentially what he did is that if the black hole horizon is smooth in the sense that if you're falling into the black hole horizon, then you don't see anything. Okay, the horizon is not like a surface of the star. So horizon is just some point in space where if you send in signal from the center and you cannot go past that point. Okay, so there's no, according to general relativity, there's no object there. Okay, so it's just simply you can just fall in. And if that's the case, if you trust general relativity, if that is the case, including quantum effect, he got the result that if you see black hole from far away, and then that far away observer will see some radiation with the temperature 1/8 pi m, exactly consistent with the Bekenstein entropy formula. Okay, so this establishes black holes are thermodynamic object. Now everything's going well. Black hole has a temperature, entropy, and so on. Okay. Now, Because as is well known, this happy situation persisted only 1 or 2 years. And his calculation says that the Hawking radiation emitted from black hole does not depend on detailed initial state. Suppose you have some black hole and you drop or form the black hole by collapsing desk or chest with the same mass. Then because of no-hair theorem, the black hole mass is the same, and final state is the same. In particular, the final state was a mixed state. So this means that the time evolution is not one-to-one, okay? So you lose the information. If time evolution is not one-to-one, we can't do regular physics. Even if you know the perfect current states, you cannot solve the equation of motion to predict the future or to solve backwards in time. You can't do that, okay? That was original version of the black hole information problem. But this is not necessarily something we are talking about in modern days, okay? Because the black hole itself provided the solution essentially to this information loss problem in the original form. As is well known, the black hole entropy goes like area. So that means that if you think about some fixed volume, and usually you can put, if the space-time is like a lattice of Planck size, then of course you can put the particle or not to put the particle in each site. And then of course 2 to the volume, take a log. Then of course entropy goes like a volume in Planck units. That's much bigger than the area in Planck units. But black hole is a final state of the evolution, okay? Gravitational collapse. So this is the highest entropy state. So a highest entropy, this volume, this region can have is much smaller than this, what you naively imagine of the Planck size lattice, okay? So all these space-time exists down to the Planck length is complete illusion, okay? Despite the fact that quantum field theory treats in this way, okay? So that means that the problem is already existing way before reaching a Planck length, okay? So quantum field theory in curved space-time must completely break down way before that. And then of course, the explicit idea of realizing this holographic principle was ADS-CFT. I don't need to review. It's D plus one dimensional theory of quantum gravity with asymptotically antidocited background. And with the fluctuating space-time inside is due to conformal field theory in the dimension, non-gravitational theory. Okay, so if you take this, then of course you can do the experiment of forming black hole and then having evaporation at the center of the ADS. Then this whole process, okay, can be mapped into conformal field theory. And conformal field theory, we know everything is okay. Okay, it's even non-gravitational theory. So it must be unitary process. So the final state of the Hawking radiation must contain information of the initial state. Of course, surprise was that in Hawking's calculation, everybody believed that his calculation was correct in the regime he computed, but actually not. So something is hidden in long distance. So according to that holographic picture, what the black hole physics Hawking radiation is. Okay? Let's imagine that if you just drop some object here, and if you drop to the black hole, and at the quantum level, the black hole horizon is emitting Hawking radiation. And because of the gravitational potential well, this Hawking radiation, most of the Hawking radiation is trapped and forming a Hawking cloud, okay, around the black hole horizon. Okay? And this Hawking cloud has a temperature, and this asymptotic Hawking radiation has 1/8 pi m. But this cloud, and this is a leakage. Leakage is the Hawking radiation. This cloud, the temperature become higher and higher and higher as you approach the horizon because of blue shift. Okay? And at some point, the temperature reach string temperature, and there suddenly a space-time picture breaks down. Okay? So this string length layer outside, just outside the horizon, you don't have a space-time picture, and around this you have a cloud. Okay? So that's the quantum mechanical structure of the black hole. Now, if you drop the object, what happens? If you drop the object, because of gravitational redshift, it's just becoming slower and slower and slower and slower. And at the point where it reaches the string temperature, then clearly this object is dissolved, and it will be absorbed into the horizon. Okay? And then that information is later coming out as a Hawking radiation. So if you view that way from far away, you certainly don't have any issue of information loss. Because if you, this is like pretty much the same as like the surface of the star. Okay, if you just send in something and if something is absorbed and staying around the horizon, and later, of course, it will emit. The certainly emission will remember what happened on the surface. But clearly, this means that the surface looks like a material surface. Then, of course, nobody's asking information loss at the surface of the star. But then the question is, if this is the case, like suggested by ADS-CFT, what's the interior? The point is that the information problem is not there because black hole horizon behaves like a material surface. Okay? If it behaves like a material surface, absorbing the things and then it's retaining the information and then sent back, then clearly no information problem, no issue with the unitarity. But then what's the interior? General relativity says that if you send in object and you are object, then you don't feel anything. You should not feel anything at the surface. You should go through. So you have to explain this emergence of the interior if you view this kind of black hole from outside, okay? And not just the existence of interior, an important thing is that why this existence of interior is specific to just the black hole, okay? Because quantum information point of view, this flow of the information is pretty much the same as other surface. But if you just if you just smash into the surface of the sun, then clearly you will see the surface, you'll be burned and so on. You don't see near empty space. So what's the point? What's the special about the black hole? And then why in the black hole case, you see the interior, like smooth interior, empty space, but in the other object, you don't see it. Okay? You have to explain this if you start from this, okay? Or on the other hand, you could take alternative view. You start from something like a general relativistic view that the black hole is just a smooth, okay, near empty interior, yeah, as suggested by general relativity. But then it's a Hawking's argument. Okay? His calculation applies, and then naively it leads to information loss. Okay? So you have to explain what was wrong with the Hawking's calculation. In any case, the point is that the problem is a contradiction between unitarity and the smooth interior. Okay, it's not just the issue of quantum information is lost and so on. Because if you take this external view, then you don't have any problem with the unitarity. Okay, then clearly only thing you lose is interior. Okay, and if you assume interior, then your Hawking's argument will tell you that information will be lost. Okay, so the claim of today's talk, okay, this is the status. So the claim is that in a quantum gravity, a system with a black hole, or more generally horizon, accommodate actually two very, very different descriptions. And it looks naively so different, but physically the two are equivalent. Okay? The claim number two is that in this thing, these two different descriptions, only one of the quantum mechanics, unitarity, or general relativity, in particular, the existence of interior spacetime is manifest. Then the other emerges as a very non-trivial dynamical or very non-trivial process, as a non-trivial process, and the other feature emerges. But the theory has both features of unitarity and smooth interior or equivalence principle. But in any one description, only one of them is relevant and completely manifest, and the other one emerges in a very intricate way. So that's the claim, and this is something we'll be looking at, and we will discuss one of the description in more detail. Okay, any question? It's probably too elementary. Okay, essentially these two descriptions corresponding to these two. Okay, the first one is like starting from unitarity. Unitarity is manifest, and then you understand the existence of interior in an intricate way. The other was starting from general relativistic spacetime, global spacetime, and then understand why the information is preserved. So let's go in the second option first. That's the picture based on global spacetime. This is not my own work, but it's good to review. And we will later see that the other approach will completely reproduce everything you will get from this approach. It's called replica wormholes or quantum extremum surface prescription and so on. Okay? So this approach starts from a global space-time. Okay? That means just usual space-time of general relativity. In particular, if you think about the black hole, you consider equal time hypersurface, which goes through both interior, inside the region of the black hole, and then outside. And you can define quantum states on this equal time surface, okay? So you have a global quantum state psi. Yeah, this is a Penrose diagram, right? Now this description, we know now that these are highly super redundant. Because if you can take, for example, the surface in which interior volume goes like infinity. You can just choose any space-like surface as an equal time surface, and this interior volume is huge, okay? Even infinite. And if it's infinite volume, if you excite the particle in different location, these quantum states are orthogonal. So clearly A dagger and A, and with a different location, it's just commute. Okay? So it seems to have huge number of, in particular, infinite number of independent quantum states on the interior, if the interior has an infinite volume. On the other hand, Bekenstein's entropy says that it's area. Okay? So the number of independent quantum states must be bounded by exponential area. So what's happening? This is a redundancy. The answer, which is suggested by a lot of calculation, is that at the semi-classical level, this volume, the huge volume, and then you excite the particle in two different locations, are certainly orthogonal. But at the level of quantum gravity, actually not completely orthogonal. It's e to the minus s over 2. Overlap is there. So if you think about psi1, psi I, psi j, overlapping matrix, and then not just a diagonal element, you have an off-diagonal element, of exponentially small off-diagonal element. But this matrix is e to the s, e to the s. So if you diagonalize it, in fact, only e to the s independent states exist. All the other is a null state. Okay. So despite the fact it semi-classically, it looks like a huge volume inside the black hole, those are almost a fake. Everything's fake, and the real dimension is bounded by e to the s. Okay? Because of this exponentially small overlap between apparently orthogonal states at the semi-classical level. So this is clearly non-perturbative effect. Unless you consider non-perturbative effect, you don't see this. So this is a saving. It's overabundant problem. So in this framework, how to understand unitarity? Okay? As it's clear, I'm taking equal time hypersurface, which goes through inside the black hole. So existence of interior is not the problem. Of course, it's manifest. I started from this global state. But then Hawking's calculation says that in this kind of view, you have a general relativistic smooth interior, and then the final state will violate unitarity. That's the Hawking's calculation. How we view this, okay? In this view, the Hawking's emission can be viewed as a pair creation of positive and negative energy particle at the horizon, and negative energy particle hit the singularity, and these things goes outside as a Hawking radiation. Okay, that means that entanglement entropy of this region, outside region R, of course, keep increasing because you have EPR pair, the one of them is gone, so you have one pair, and then the next particle, and keep adding. Okay? So entanglement entropy, von Neumann entropy, defined in this way, it's essentially number of EPR pair whose partner is not in R, so then it's keep increasing. Okay? That means that finally it becomes a mixed state and completely violate unitarity. Okay? So what we have to get instead is that if your black hole is completely evaporated, then the state is on here because black hole is already gone. So this state, you can't have any particle whose pair is R bar because R is everything. Okay? The black hole is gone. So outside the black hole is everything. So that means that any EPR pair or anything must be partners inside R. Okay? So that means R itself is a pure state. So you have to go back. Okay? So this is, of course, famous page curve derived in 93. So you have to understand why you get this curve rather than Hawking's result. Okay? In this way of viewing black hole system, you start from global space-time, global state, and despite that, despite this pair creation, keep being pair created, you have to, this curve must go back. Okay? So how to get this? Okay? That's the thing which developed by these people. Okay? So let's start from this global spacetime, and you keep computing is von Neumann entropy of the region R. You can do this by, you take instantaneous some spatial slice, and you go to the Euclidean space, and here's R, here's R bar, okay? And then in Euclidean space, you can calculate density matrix by specifying the field configuration here and there, right? Because it's a bra and a cat, because state is completely specified by a field configuration. So you can specify here and there. So that's the GIFI element of the wave function now. So you can compute it, okay? And then you have to compute this trace law, log law of this density matrix law. But you don't want to deal with, of course, this log law. So usual replica trick, you can go to the law to the n, and then take n goes to 1 minute, okay? So then this is certainly just mathematical equation. So what you have to compute is a log to the n, okay? And then you can analytically continue log square, log cube, log to the fourth, and log to the fifth, and then take n goes to 1 limit, and then you can get the von Neumann entropy. So now let's calculate, for example, rho square. So how to compute the rho square, okay? To compute rho square, you just have to double this seat, because this seat represents rho. So you take rho square, okay? And then you just equate rho and column and rho, right? So you can go back, and that's a rho square. And if you do this, and you do the analogous thing for n equals 3, and then you get the rho cube, and n equals 4, you get the rho to the fourth, and you plug in this formula and get the von Neumann entropy, you precisely get the Hawking's result. Okay? But what these guys said is, now the theory is gravitational. The only thing you have to do is to specify boundary condition on R to calculate replica trick. So you have to include all possible space-time configuration, including wormhole connecting these two seats. Okay? It is crazy, because these two seats are not the physical space-time. Physical space-time is one seat, of course. It's just our space-time. To compute rho square, you artificially copied into rho square, but you have to include some new contribution of the wormhole connecting these two, okay? And if you include this, what you get is this page curve. Yeah, so this is a calculation you have to do if you want to see the unitary properties. And we know much more, yeah? So this is a way to compute essentially average of the von Neumann entropy. Okay? Each microstate has a von Neumann entropy going down, and this way you can get the average of the von Neumann entropy. So that's average of this curve is this curve. Okay. On the other hand, Hawking's calculation corresponds to first take an average and consider average state, and then compute the von Neumann entropy of the average state, not the average of the von Neumann entropy. You compute the von Neumann entropy of the average state, then you get this, and that's of course nothing wrong, okay? Because you're not talking about microstates. Okay, so so this is clearly showing that, in fact, more physical term, what's happening is that this pair, right, the Hawking's process is like a pair creation. So that means at the later stage, this particle, Hawking particle, is paired with this interior partner, okay, because that's the pair creation process. But on the other hand, to go back, to have a von Neumann entropy going back, and then these later Hawking radiation must be entangled with the early radiation to go back to the pure states. So this particle must be entangled with both earlier emission and then partner, but single particle cannot entangle with the two different things. Okay? So this is a monogamy of entanglement. So this means that this early Hawking radiation and the interior degrees of freedom is hiddenly same object. Okay? And this was, many people said that, but in a most clear way, the Mardasena and Saskin named this as an ER equal EPR, and the fact that it's completely non-local. Okay? So this degrees of freedom at the early Hawking radiation, which is now far away from the black hole, and black hole interior degrees of freedom is hiddenly the same degrees of freedom. Yeah? Otherwise, you won't get this phenomenon. And of course, hindsight, this is of course obvious, because if the Hawking radiation contains full information about the unfolding object later, and then general relativity allows to slice in this way. So unfolding object, of course, generally, according to general relativity, it's just going into the black hole. Okay? And if Hawking radiation contains full information about unfolding object, then on this slice, you have information doubling, copying, which is prohibited by quantum mechanics. So that means that these 2 degrees of freedom non-locally must be the same degrees of freedom, in fact. Okay, so this is another manifestation that the description based on global spacetime of the general relativity is highly redundant. Okay, at the long distances. So you are overcounting the same degrees of freedom here and there to many places. Okay, so the bottom line of this description is that you can start from global spacetime. Okay, which goes through interior. So in other words, general relativity starting point. Okay? But then Hawking's calculation naively says that unitarity is violated, but it's not the case. If you think about the clever non-perturbative effect of gravity, say replica wormholes in my presentation, then you get the page curve, which is unitary. So the only interior is manifest at the beginning. It seems like the theory doesn't have any unitarity, as Hawking's concluded, but it's not. If you think about the non-perturbative effect of gravity, in fact, the theory had hiddenly unitarity. Okay, so that's one way to understand black hole physics. But now I claim that you can understand exactly the same physics from completely the opposite direction. You can start from manifestly unitary description and then understand the existence of interior, okay, as an emergent phenomenon. Okay, so what this description is? This description is essentially holographic. Namely, if you view the black hole from far away, as I said, essentially there's no problem in information, because if you drop it, this object even won't go into the horizon because of time delay. If you're looking at from far away, the object slows down, and you have a Hawking cloud whose temperature is blue shifted near the horizon, okay, the string temperature. Therefore, this object is dissolved, okay, it's burned, the string temperature, and then absorbed into the horizon. And because it's on the horizon, and when it's emitted, there's no information loss. Things are there, stays there, and come back. That's it. Okay? So that's the same as, for example, the surface of any regular material. Okay? So this is manifestly completely unitary. This is a description based on boundary picture in area safety. But then the question you have to address is that why this object feels that there was nothing on the surface and it just goes through. Okay? Moreover, what you have to understand is why that's the case for black hole, but not the case in a regular material surface. Because information flow-wise, it's completely same. Okay? You have a surface, black hole's horizon looks like a material surface. Okay? And I claim that there are 2 key features defining black hole as a very special object, which allows you to have a description based on near empty spacetime. Okay? The first is because of gravitational redshift, things are redshifted, and then the state is now exponentially dense. Okay? The exponentially dense state, you cannot discriminate, because to discriminate exponentially dense state, which is a black hole microstate, to distinguish these states, you need exponentially long time, clearly. It's delta T, delta E, it's h bar r. But you don't have exponentially long time for realistic black hole. By the time you wait exponentially long time, of course, everything's evaporated. So only thing you can access is the Hawking radiation, the final state Hawking radiation. So to talk about the black hole, what happens if you're falling into the black hole and so on, you can't discriminate all these fine exponentially, only exponentially separated modes. Okay, but on the other hand, of course, high energy excitation, black hole, you have a black hole vacuum, and then you just throw in baseball. Of course, baseball is very large excitation. Those things you can discriminate. So let's separate the mode in this Hawking cloud region. It's sometimes called zone, or sometimes called atmosphere. The black hole, in the short shield case, this is 2m, and this is around 3m. And this region mode in this region, let's separate into the two. One is a hard, I call hard mode, whose frequency is essentially the gap of the excitation is bigger than Hawking temperature, which you can discriminate clearly, okay, in a time scale. And the soft one is this exponentially dense, what you could call black hole microstates. You can't discriminate. Yeah? You don't have enough time to even discriminate these things. So let's consider this hard mode and a soft mode. And so hard mode is essentially some object, okay, which semi-classical theory describes. And soft mode is something semi-classical theory can't resolve. So essentially the state of the cloud or microstate. Okay, this is just a name. And this region, I don't have to do this because there is no cloud. So this far away, outside the zone, just a simple quantum field theory treatment. So I just think about these three possible modes and then ask what happens to these three modes in the black hole. The second characteristic feature of the black hole is that the black hole horizon around there, the blue shifted or local temperature is a string scale. So it's a string dynamics is there. It's called stretched horizon. And there are many analyses by many of the feature of this dynamics of stretched horizon or string scale dynamics. And that's completely chaotic. It's saturated the Lyapunov exponent and so on. It's completely chaotic. And this chaotic state is indeed reached quite quickly. So that's called a fast scrambling. So if something is dropped and then approached to the stretched horizon where the local temperature is string, so very high temperature, then things are resolved and completely mixed around the horizon right away. Okay? So M log M in the case of Schwarzschild. And it's chaotic. And in fact, those dynamics is universal as well. Namely, it doesn't discriminate low energy species. Photon, electron, neutrino, and everything is just scrambled right away. Okay? And these features are crucial. Okay? And because of these features, I would claim that interior, if you are the object, okay, going into the black hole horizon, and then you see near empty spacetime. Okay? And this is not the case in regular surface of the sun, for example, right? So this stringy ultraviolet effect is the origin of interior. You will see that. So roughly speaking, what happened is that, let's think about the black hole vacuum state. There's no excitation, no object. And then I split the mode into hard and soft. And you have a lot of states. And suppose you have a black hole of mass m. That means that the state has complete energy m. But it's possible that the hard mode is excited as long as soft mode is de-excited. Okay? So full state can have an energy m, and this energy m can be distributed differently between hard and soft mode. And chaotic feature says that all these possible terms arises with the essentially same coefficient. Okay? And given this, if that's the case, this state looks like a thermophile double state. I will go through more math. And we certainly know that even in a Minkowski vacuum, in a Lindner frame, it can be viewed as a thermophile double state, thermal states. And then in this case, you can use this map differently, the other way. So if the state looks like a thermophile double, and then you can change the frame, and you can claim, or you can see that you have an operator which describes near empty vacuum states. Okay, that's what's going on. And in fact, here in all these soft and radiation is the early, you'll see that the early radiation degrees of freedom is involved in constructing interior space. So let's just go to like more math behind this claim. So what's the black hole vacuum state? Okay? The black hole vacuum state is not the vacuum of corner gravity, certainly excited state. Okay, so black hole vacuum is just no object. Okay, like no baseball or no electron around the black hole. So black hole vacuum state is specified by the states of the hard mode and the states of the soft mode and the state of the far mode. Okay, so this is essentially the structure. Because I just specified, I just classify the possible modes into three. Okay, with a hard mode and soft mode and far mode. And even if hard mode is excited, this is occupation number, is excited, soft mode can be de-excited. And as long as entire state has a mass m, then all these are realized, all these terms are realized with the essentially same probability. That's the chaos, that's the result of the chaos. Okay? If you have a chaos, and this coefficient is just quadratically distributed with the size specified by just a number of states. Okay. Then the point is, if this hard mode, something you can describe by semi-classical theory, is excited by energy E, then the soft mode state must have energy m minus E, okay, to compensate, to go to mass m. And that means that the number of possible states of soft mode is small, okay, because e to the s, Bekenstein-Hawking, with energy m minus E. Okay? So the number of terms corresponding to excited hard mode is small. So if you canonically normalize these states, and then you get the Boltzmann factor. So let's go to, so if you look at these states, and this hard mode is a mode which has energy, excitation energy, hard enough to be discriminated as a material. So you can define creation annihilation operator acting on this hard mode in a zone region. Okay, so that's the zone region. But then, because you can't discriminate these soft and the radiation states, you can't discriminate this microscopic index I. Okay, so you see these states, which is entangled with the hard mode, different hard mode state, as the same coarse-grained state. Okay. I know that this is kind of too quick, but so let's define this state, which is entangled with the hard mode configuration specified by occupation number n. The state which is entangled with this n, let's call this as a double cap n, okay, which depends on black hole microstate A. Okay, this coefficient is a black hole microstate. Okay, but then this state is not canonically normalized, so you can just normalize, and then normalization constant you can work out, and then normalization, if you rewrite this entire black hole state in terms of coarse-grained states, this is the form you get. Exactly the form of thermophile double states. E to the minus E. En is the energy of the hard mode state over 2th. Okay? And because this is exactly thermophile double states, and you can define operator acting on this double ket state. Remember, double ket state is nothing other than coarse-grained states of the black hole soft mode and then far mode radiation. Those things is the second exterior, effectively, because this is a thermophile double form. Okay? And you can define the operator acting on this double ket states, and then you can construct interior operators in a standard two-sided black hole. Okay? And this construction can be done because of the chaotic distribution of the coefficient. This C is completely chaotic distributed. That's the only assumption I took. It's a completely chaotic distribution will lead to this Boltzmann factor, the correct Boltzmann factor that was crucial to go to the interior picture. So you can't do the same construction for the surface of the sun and the surface of the material or anything like that. So it's a very specific property of the black hole, which is a chaotic surface, okay? And this is detail, so I may probably skip it. You can read the paper if you're interested. And this itself is not completely sufficient because creation annihilation operator in the second exterior was depending on the microstate in a precise way. You need to know the microstate to construct this operator, but you don't know. Yeah? But you can promote this operator into just summing the operator we constructed to the sum of all these microstates. You can sum up with the A, and then you can construct some more stable global promoted operators. And then you can just reconstruct this interior. Okay, so so what is shown by this construction is that if you view the black hole from far away, then unitarity is not the problem. And as long as you focus on high enough energy excitation, which you can in principle discriminate, then you can rewrite the states in the form of a thermophile double. And because you can write down some field double states, and you can view this as a two-sided black hole, and then you can describe interior in a standard Bogoliubov transformation way. Okay? And this description is intrinsically semi-classical because I'm focusing only on the hard mode, and all these soft mode states is effectively playing a role of the second exterior. Okay? Here. So this is really black hole interior is a semi-classical concept, but with that you can just reconstruct the interior. And now this concept, the good thing about this construction, it's analogous to some earlier work like this, and Raju and Bernindez and myself and so on. But precise identification is different. But now I precisely identify the first exterior degrees of freedom. You can write down as a hard mode. Everything else is what's entangled with the hard mode. You can analyze this effective interior theory, the property of effective interior theories, just by using the assumption that the coefficient is completely random, okay? The Gaussian randomly distributed. The first property you can get is that this construction itself has an ambiguity of order e to the minus s, essentially. And it must be, because black hole is a finite dimensional system, e to the s Bekenstein-Hawking. So you don't have any infinite precision. You can't have infinite precision measurement. So this effective theory itself has intrinsic ambiguity of e to the minus s. And also black hole operators, I constructed operators describing black hole interior that can cover e to the c times some coefficient times entropy. E to the cs number of microstate is covered by single global interior operators, but c cannot be exponentially close to 1. So it covers only exponentially small, because e to the 0.9 s Bekenstein-Hawking is exponentially smaller than e to the s Bekenstein-Hawking. So it's only exponentially small region of the full black hole microstate is covered. So you need a set of operators to cover entire microstates, and that's the statement of state dependence emphasized by Papadopoulos and Raju. Okay, and you can see this clearly just by using assumption that the coefficient is quadratically just Gaussian distributed randomly, and you see all these properties. And the final thing is that black hole interior arises from, because it's hard mode and entangled thing is soft and radiation. So black hole interior involves both radiation emitted earlier and a soft mode. But as long as black hole is young, which is before page time, then you can use certain called Petz map to reduce operator to act only on black hole clouds. Okay? So you don't need to involve radiation emitted earlier if the black hole is young, and then you can construct the interior without involving radiation. But if black hole is old, past the Hawking page time, after page time, you must also involve early radiation to construct interior. This is a manifestation of ER-EPR in this construction. And you can get all these property we found in entanglement wedge or replica wormhole construction from the different way. Why you have the big, apparently big semi-classical volume in a black hole interior, and you can have many independent states, despite the fact that you have only e to the s independent microstates. And you can understand that as, if you think about generic black hole microstate, e to the s term with the coefficient is square root 1 over square root e to the s, and then you take two generic states and you take inner product. Then inner product goes like this, okay? And then size of the coefficient is 1 over square root e to the s and 1 over square root e to the s. So these coefficients 1 over e to the s, and then summing up e to the s terms, but the phase is random, right? Okay, the two generic state phase is random, so it's only square root, and then it's e to the minus s over 2. So it's essentially any states are orthogonal. So you look like approximately many double exponentially many microstates.
Yes, you know, you have 5 minutes.
Okay, yeah. And the other thing is that in wormhole calculation, this I don't have time to explain, like a wormhole calculation seems to show that the black hole wormhole calculation is always ensemble, because if you think about the psi I, psi j, states, then it's 0, but the square of the 0, you get something non-zero in ensemble nature calculation. But this you can understand in this picture, it's completely obvious because soft mode, you cannot discriminate. So you have to average over soft mode states, and that will completely reproduce what they got in their calculation. And finally, for, I don't know, experts, and this construction says that you have a black hole object throwing into the black hole, and then black hole interior shows up essentially with a black hole cloud and then early Hawking radiation. You involve both these coherent excitation of these modes in interior. But this seems to be at odds with the statement of entanglement wedge reconstruction. If you heard, like radiation only allows you to reconstruct the interior at the late time. But this is not inconsistent because radiation at the time t involves information about radiation plus this cloud soft mode at the earlier time because of Hawking radiation. Hawking radiation send the information in soft mode to the radiation at late times. And then using this radiation, you can reconstruct the interior of the earlier time. That's why entanglement wedge is, of course, scrambling time earlier than the radiation. This is completely consistent. And in fact, this entanglement wedge reconstruction is nothing other than a statement of Hayden-Preskill. Okay, it's just literally it's just that. Yeah, if you wait the scrambling time, you can reconstruct the period. Okay. So summarizing this picture, you can get exactly the same feature starting from manifestly unitary description. You view the black hole from exterior and you drop the object, and then surface, black hole horizon behaves like a material surface, and then later come back. So it's just completely unitary. To understand the interior, this chaotic nature of the black hole horizon, okay, the blue shifted horizon, has a string temperature, and that will reveal universal thermalization dynamics, albeit in a red-shifted form. And because of this chaos, if you use the state is chaotic, just by that assumption, you can construct the interior operators. And so the emergence of this interior thing is really like result of UV chaotic physics involving black hole soft hairs, soft modes. And this is a way you view black hole physics in this way. But the conclusion is the same. So structure of the quantum gravity, you can start from, say, general relativistic picture. That's the first one. You can start from just a global state. Okay? The state, quantum state, is defined on this surface, which goes both interior, inside and outside of the black hole. It's called nice slice. And then, of course, existence of interior is obvious because you start from global spacetime. But this description is highly, highly redundant. The two apparently different degrees of freedom is hidden the same degrees of freedom. So you have to divide out, okay, to get the full unitary picture. Okay? And the way to divide out is to include this replica wormhole in a path integral. If you include this contribution, extra contribution, you get the unitarity back. Okay? On the other hand, you can start from unitary construction. Okay? You view the black hole from exterior, you send in the object, stays on the horizon, coming back, and then interior arises emergently from the soft mode and the radiation as a coherent excitations, which I kind of showed explicit construction of operator, but essentially black hole microstates and then Hawking radiation emitted earlier time behave like black hole interior. Okay? If you are dropped, then those modes coherently react to you in such a way that you seems to feel there was nothing at the horizon. Okay? So that's a miraculous mechanism why such a thing happens. But only chaotic dynamics is what you need. So ultimately, why these kind of completely different description exists is just gauge redundancy of the black hole. Usual general covariance is the perturbative redundancy of the description. Of course, you can change the coordinate to describe the same physics, but even black hole has, quantum gravity has a non-perturbative redundancies, even different topology can have the same state, right? State is defined by space-time, and you can slice in a different way, equal time. Just definition of equal time slice is just a different gauge. And then sometimes just a singly connected state looks like not simply connected states. And those are studied recently in detail. So this is just summarizing slide. So if you think about the black hole problem carefully, long distance problem, not the Planck distance problem, and then we're just learning a lot about the structure of the quantum gravity. In particular, my message first is that you have two very different descriptions of the same physics. The first one is based on global spacetime. So it's like a general relativistic friendly description. You have black hole, the black hole has interior, of course, starting from that, but then naively, it doesn't seem to be unitary, as Hawking concluded. But if you include the non-perturbative effect of gravity, you actually see that the quantum gravity is still unitary. Okay? The one example was replica wormhole in 1+1 dimension. The other thing is start from unitary holographic description. If you take ADS CFT, black hole formation and evaporation is clearly unitary because this is a process of CFT. Okay? But then why it's unitary? Because black hole horizon behaves like a surface. Okay? The things are not, these things are just absorbed into there and stays there and coming back. It's clearly unitary. But then why, if you are jumping into the horizon, you don't feel anything? That you have to understand in a subtle way. That was a collective excitation of early Hawking radiation and soft mode. And I probably was too quick, but I showed that you can build the interior from these degrees of freedom as a collective phenomenon. But the theory itself has both features. Okay? Only one of them is manifest, depending on the starting point. And the other arises as a very tricky, strange phenomenon. But this is nothing other than, like, in a case of gauge theories, unitary gauge, and then of course, Lorentz gauge looks like a completely different description. But in fact, the theory is Lorentz invariant and of course unitary. And the same thing is happening at the non-perturbative level in quantum gravity. And to me, this was why quantum gravity was actually difficult. Quantum gravity, quantum mechanics, and general relativity both are there. But in fact, in one description, only one of them was relevant. So that's why it's a Hawking's information loss problem, or like the firewall problem. Okay? That's the problem which interior may not exist. The firewall description is like this. Okay? The Hawking description is like this. Okay? But if you, by doing it carefully, you can work out these things without knowing the detailed microscopic physics at the Planck length. Although we also are interested in knowing Planck scale physics, of course. That's it. That's all I say today.
Okay, thank you very much for this nice presentation. We still have some time for questions. So is there any question? Please feel free.
I have a very naive question. Concerning the global space-time picture. Somehow, can you justify the use of the replica trick?
Yes, replica trick. Replica trick is just a trick.
Replica method. I think replica you can always
it's just a simply pathing the method to compute the rho square and rho cube.
But if I understand correctly, you cannot use the replica trick anytime.
Replica. So replica wormhole or replica trick? Which one?
Replica trick.
Replica trick is just literally just a pathing theorem to compute states, and you do this pathing theorem with the specified browser and ket. And if you want to compute the square of that matrix, you just prepare this twice, and then set the column and row to be equal. Just row square, okay, row ij, row ji. Diagrammatically, that's just the replica trick.
Okay.
So replica trick is just trick. It's always you can do. But to compute row square, this is the usual trick. You prepare the two row, and then you contract the index in such a way that you're computing a trace row square. But if you naively do that, and then you get the Hawking's answer. After you use this row square row cube, you calculate the Von Neumann entropy, you get the Hawking's answer. But if you introduce this replica wormhole connecting two different sheets, which you artificially introduce to compute rho square, and you include that geometry new term in a path integral, then you get the unitary answer.
Okay, okay. Thank you.
That's the replica wormhole. Replica trick itself is always just a trick. But what kind of geometry you have to include, and then claim is that if you include this wormhole geometry, you get the unitary answer, despite the fact that naively it's not unitary.
Okay, thank you.
Yeah, so this is a way to reconcile these two things in this way. Okay? This has a completely different way, but my claim is if you ask any physical question, you get the completely same answer. But it's completely different way, you get the same physical answer. That is essentially the claim.
Very interesting. Thank you very much.
Okay, any other questions or comments? Well, then I suggest that we thank the speaker.
I have a small.
Oh, okay. Sorry, I was too quick. Suelma, go ahead. Please go ahead.
Yeah, I have a small question. You mentioned that the chaotic nature of this horizon gives rise to the Boltzmann factor.
Yeah.
Yeah. So what would be the calculational detail in that case? Where can I find?
Oh yeah, I think I was way too quick. But let's see. Suppose this is a hard mode state. And you can consider hard mode, which is like a baseball or something on the near black hole region. Okay. So now if this state, you can have some vacuum state of the hard mode, or hard mode is one excited hard mode state, and two excited hard mode states, and three excited hard mode states, and then corresponding soft mode states has energy m or m minus e. E is excitation energy, and e minus 2e, and e minus 3e. Okay, so then how many independent microstates you can have with a given energy? That's e to the s Bekenstein-Hawking 4 pi m minus e square.
I see.
Yeah, because e to the 4 pi m square is a Bekenstein-Hawking entropy. But soft mode has energy only m minus 2e or m minus 3e or m minus 4e. Okay, if the corresponding hard mode is excited. So the number of terms is small. If hard mode is excited, number of terms, number of independent states of the soft mode is small. And then all coefficient is the same size. So if you normalize these soft mode states, if the number of terms is small, then the normalized states times small number. That's the coefficient. And then if you just rewrite these states, okay, this entire thing, which is entangled with the hard mode state configuration n, which is excitation number, I simplified into one species, and so 0, 1, 2, 3, 4, and then m minus e, m minus 2e, m minus 3e, and those things, the number of independent term is different for the one entangled with the vacuum states or entangled with the first excited states and so on. So this normalization factor is different. And this normalization factor would precisely give this exponential minus e over 2t. So exactly the sum of the double states. And this, you need to assume only this randomly distributed C. You don't need any detailed information. You can really like get this. And yet you need randomly distributed C. So if in a case of surface of the sun, clearly photon is thermalized, but neutrino is not. Neutrino is going through. So neutrino doesn't have this C in this form. But to get this sum-free double state to two-sided picture or Bogoliubov transformation, all the species must take this form, right? That's almost impossible in any realistic material except for black hole. Because of this huge inclusive temperature, the string doesn't discriminate. It's a very specific dynamics. So that's the message. So black hole is very special. Thanks.
Thank you very much. Thanks.
Way too quick. I understand.
Thanks.
Okay, I think we have come to the end of this section. So I would like to thank all the speakers, well, including myself, for giving a nice presentation. And it's now 3 o'clock in the middle of the night in the Netherlands, so it's time to go to bed. But tomorrow is the next day, and then it starts at 15:10 Greenwich Mean Time with the next session. So I wish you, again, thank you all very much for this presentations, and well, either good morning or good night or good, I don't know where you are on the world, but